G'day chemistry students. In this video we're going to be looking at dot points 5.2.1 and 2. And in particular we're focusing on this new concept called Chateliers Principle, and we're going to start to talk about how that's related to our collision theory concepts that we've been looking at over the last couple of modules. Let's get into it. So for Chateliers Principle, what it says is that if a system is at equilibrium and there's a change that happens to the conditions of that system, then what the products and reactants, the chemicals that are inside, are going to do is try to balance out whatever change actually happens. So if we were to change the concentration, temperature, or the pressure of a system, then what all of those chemicals are going to try and do is oppose that change and try to bring things back to the way that they were, to recalibrate themselves and come to equilibrium again. So we can actually use Le Chatelier's principle to make predictions for what would actually happen to a system if a change was put on it. So what we can look at is what change actually happened. Was the concentration of maybe one of the reactants changed, or did the temperature of the chemicals increase? The next question is, well, what's the opposite of that change? Because that's what the system's going to try and do. So if there was a decrease in reactants, for example, then the system is going to want to try and bring that concentration back up. If there's a change in temperature, then the system is going to want to try and counterbalance by opposing that temperature change. What we then need to look at is, well, in the equilibrium reaction, what direction is favored? Because the direction which opposes the change is going to be the direction that's favored, the one that's going to be reacting more, the reaction rate's going to increase. What we're then going to say is there a shift to the left or the right? That's usually how we describe what direction is favored. We say it shifts to the left or it shifts to the right. And then what we can do is predict what changes would happen to the concentration of the products and reactants as a result of whatever shift has occurred. And you can find that series of steps in our textbook. So I'm going to go through a couple of examples of how to sort of run through those 5 questions and make predictions for real life examples. Again, we're going to use our nitrogen dioxide and our dinitrogen tetroxide example. So we're going to have a system of those two gases in a container at perfect equilibrium. Everything's balanced out, everything is happy. But what I'm going to do in this first example is add NO2. In other words, increase its concentration. So if we start running through the questions, the opposite of that change that I have imposed on the system is to reduce the concentration of NO2 in response. The next question then becomes, what direction would be favored? That's going to be the one that reduces the concentration of NO2, the one that consumes NO2. So that's the forward process. And that is a right shift. We're shifting in the right direction. So as a result, if there's going to be more reactions in the right direction, less reactions in the left direction, what we're expecting is for there to be a reduction in the concentration of nitrogen dioxide and an increase in the concentration of dinitrogen tetroxide. Similarly, we could make some changes by altering the temperature of the system. You'll note here that I've put an annotation next to the reaction equation. It says that delta H is negative. If you see this next to an equilibrium, what that means is you're being told what the enthalpy change will be for the forward process. Usually it would be a number, but we really only care about the polarity. So in this case, delta H is a negative number, which means that the forward process here is exothermic. Heat is being released. So anyway, if we heat the mixture up, what we would need to have happen is for the gas to cool down to reach thermal equilibrium again. So the question becomes, well, what reaction direction is favored? That's going to be the endothermic process, the process which is going to end up consuming a lot of the added heat. And that, according to our information up the top, is going to be our reverse process, the process which will have a positive delta H. That means that we've got a left shift, a shift towards the left side of the equation, meaning that we have an increase in the concentration of our reactants, our NO2, and a decrease in the concentration of our dinitrogen tetroxide, our product. And in the final example here, what I have is a compression. In other words, a decrease in the volume that the container has, meaning that the pressure of the gas will also increase. What the system is going to want to do is try to oppose that change by reducing the pressure that's in the container. And to reduce the pressure, what's going to need to happen is that the number of particles in total inside the container need to reduce as well. What that's going to mean is that we're going to see a favor towards the forward reaction, because the products only contain one particle for every two reactant particles. So by shifting towards the right here, what we're going to end up having is a reduction in the number of particles. What that means is, again, reduction in concentration of reactants, increase in concentration of products. We can actually use collision theory to explain all three of the examples, those scenarios that I outlined above, to explain how the Chateliers principle works. And just in general, when we make a change to the system, that may lead to either the forward or reverse process, reducing the number of successful collisions that are happening. And then for the opposite process, it may also increase the number of successful collisions that are happening. It just depends on what kind of change is being made. So if you're changing the number of successful collisions in either the forward and or the reverse direction, what that's going to mean is that the reaction rates of the forward and or the reverse process will change as well, which means that the system is no longer in equilibrium. It's going to have to settle itself out again until we reach that point of equilibrium where the reaction rates are equal again. So in other words, collision theory is able to support this Chateliers principle. I'm going to break that down in much further detail for each individual changes to concentration, temperature, and volume pressure. And that's going to be in our following 3 videos. So in saying that, the next video we're going to be looking at is explaining the Chateliers principle in terms of what happens when there's concentration changes, looking at it a little bit more in depth with the lens of collision theory. But until then, have a good one.